So maybe the most important thing to know to start off with is what equilibrium is in the first place. So equilibrium is the point in a chemical reaction where the concentration of the products and the concentration of the reactants are remaining constant with time. However, don't be confused because equilibrium is dynamic. Just because it reaches equilibrium does not mean that the reaction just stops. It keeps going, but the rate at which it goes allows for the products and the reactants to remain at a constant concentration. So now that we actually know what equilibrium is, we can use that information to find an equilibrium constant K. Now first we're going to look at a generic chemical reaction here according to the law of mass action. So to find our equilibrium constant K, we're going to take K equals, now we're going to have to take the products over the reactants. So here are our products, and take C times D, and then we need our reactants in the bottom. So A times D, and then with our coefficients, we're going to use them as powers. So J, K, L, and M. And that is how you would assemble the equation to find your equilibrium constant K given a chemical reaction equation. So when it comes to the phases of matter in an equilibrium equation, you have to make sure you're not working with any solids or liquids. You can only use these equations using compounds that are in the gas or aqueous solution form. Now with that out of the way, let's take a look at what this will look like in an actual chemical equation. So first, we're going to take the products, put them here, and then we're going to take the reactants, and then just like before, we're going to use the coefficients as exponents. And as you can see, you have a similar equation to what we got from the generic equation. However, now you can see it with actual compounds and numbers. Now with everything we've learned so far, let's try to put it all together to find an actual K value when given concentrations for the compounds. So with these given concentrations, what we can do is we can actually plug in numbers into this equation and find an actual number for K. So it's still products over reactants, so we only have one product, so it's going to be the 3.1 times 10 to the negative 2 raised to the second power, like so. And then for our reactants, we're going to have 8.5 times 10 to the negative 1 raised to the first power, so we don't need to put anything there. And then 3.1 times 10 to the negative 3 raised to the third power. Now if you were to take out your calculator and put that all together, you would find K would equal 3.8 times 10 to the fourth power. Now what if we were to do something to this equation, like for example, switch the products and the reactants? So by reversing this equation, we're going to get an inverse K, because if you imagine it, it's still products over reactants, but because we switch them, it's as if we switch the numbers for this original K value, making this new equation's K 1 over the original K, which is going to be 1 over 3.8 times 10 to the 4th, which is going to equal 2.6 times 10 to the negative 5 power. So therefore, we can see that a reaction written in reverse has a reciprocal equilibrium equation. So what would happen if we did something to the coefficients in front of our compounds in this equation? Let's say we divide everything in half. So instead of 3 and 2, we have 3 halves, 1 half, and because 2 divided by 2 is 1, nothing in front of there. What you do when you change the coefficients is you take your original K and you raise it to the power that you divided by. So k to the 1/2 is the same thing as square root. So k to the 1/2 is going to equal the square root of 3.8 times 10 to the 4th, and our UK is going to equal 1.9 times 10 to the 2nd power. Simply put, we can now call this k new equals k original raised to the power of n. So something important to know is that an equilibrium constant is going to remain the same no matter what the equilibrium concentrations are for an equation, because the ratios will always remain the same. So something else that we can do using the equilibrium constant in this type of equation is find an equilibrium constant using pressures rather than concentrations. So just like before, we're going to put the products over the reactants. And with that, we can find the K value to equal 1.9 times 10 to the 3rd. So now that we know what both Kc and Kp are, which is the K value from concentration and the K value from pressure, we can use either one of these to find a K value using this equation right here, with R being a constant and delta N being the product minus the reactants in relation to the moles. So let's see if we can find K using this Kp down here at 25 degrees Celsius. So using this information, we can rearrange the equation so that K is on this side and Kp is on this side, and we can plug all of the information we have in. You now have a strong foundation for how to deal with equilibrium equations and K constants. So remember that science never sleeps, but you definitely should before the AP exam.